and smelling bad. Austin's basically barely evolved.
All right. I still haven't decided whether we're going out or not. We've been outside, it's kind of cloudy. Forecast is it's supposed to get better. But I don't know when that's going to happen. Austin.
He's here.
He's here. He just went to the restroom.
He's not there. Taylor. Joshua. Yeah. Oh, yeah. Oh, yeah. Yeah.
I need to get the Bible.
Rachel. All right, how did the homework go? Good. Okay, and you made your nice 3D drawings?
Quote unquote nice.
3D looking drawing. Oh, this looks good.
Looking like this.
Turn them in, please.
Mine only looks better because if I was putting very small, it would look great. That's the piece from last week.
Oh, yeah, let's make it flat. Last week's homework. And I want this week. Yeah.
Oh, all right.
Okay. All right, like I said, we're gonna wait until 6:30, then I'm gonna make a call. Right now, it's cloudy. But the weather forecast says it's gonna clear for a little while and it's gonna get cloudy again. I thought, well, we might get like 2-hour window, which is all we really need if it's good. So, boy, I have a spotter out there that's gonna let me know. I do not. As long as your name's on all of it, you'd probably be okay. Oh, here's one.
I'm not afraid of Mike. I'm not afraid of falling. Well.
All right. Tonight, we're going to talk about first, I want to cover something I was supposed to cover last week, and I got long-winded and took too long, so I didn't get to it. Let's talk about precession. What is precession?
We don't know the precise.
That's pretty close. I mean, there's a way more technical one, but that's pretty close for what we're going with.
Oh.
I have a
Rotation of the axis of rotation of Earth.
Oh.
the rotation of Earth's
Axis of Earth.
axis of rotation. Exactly. I have a pretty high-end spinning top here. And it's like $300, which I wouldn't buy it myself, but university can afford it. So it's kind of cool because it spins it up. You don't have to spin it up yourself. You can hear it. It sounds like a miniature kid and you're spinning up.
I remember it didn't work when we were in RTO.
Oh, yeah, I bought a new one. Oh, this one I think I'm not gonna let anybody else use.
Yeah.
Because the problem is it's great, but it's high precision, meaning you drop it once and it gets, that axis gets bent and it just doesn't work, but this works very well. You do it. All right, so the spinning top here acts like the Earth's axis. What's our tilt? 5 degrees from what?
From 90.
From 90, what's 90?
Sure
It's
he does.
space. Space, you can make it anywhere you want. So how can you say it's
From
Tilted.
the plane of Earth's rotation around the sun.
okay? What do we call that?
The actual ecliptic.
The ecliptic plane, yes.
Yeah.
The ecliptic plane is defined by Earth's path around the sun, right? It actually creates a plane. It's a ellipse. Okay? If we make something perpendicular to that, a line perpendicular to that, our tilt is 23.5 degrees off of that perpendicular. Are other planets tilted?
Yeah. Not many.
Are there any tilted similar to the Earth, close to 20 something? You guys took astronomy 1304, didn't you? So let's, you did, but you don't remember?
Not very true.
Oh, you're in it right now? Mars is very
Oh,
close.
I didn't know.
So is Saturn. I think somebody said it over here. Jupiter is almost straight up. It's like only 5 degrees off. It has hardly any tilt. Okay? So it depends on the planet. So what is precession?
The change in the direction of Earth's axis. Of the
With
tilt.
respect to the,
Ecliptic.
okay,
Ecliptic
and
plane.
the celestial sphere, right? Okay. What that means is right now, where's the North Celestial Pole pointing? Close to what star?
Polaris.
Polaris, yeah, it's actually not quite there. It's like 0.7 degrees off. It's less than a degree off. But that changes with time. This, you notice it gets lower and lower. That's because it's slowing down. If you kept it spinning all the time, it would never get lower. It would just stay at that angle precession forever. That's the way the Earth is because there's no friction in space. It's spinning. Our spin came from when it was formed. There was an angular momentum. The cloud had formed out, it's spinning, and that makes it spin.
Actually, don't know what it is.
Yeah, you start to get nervous, like it's gonna fall.
Especially after you just said you don't want it to fall.
I don't want it to fall, but I trust physics. Now, eventually it will fall, but it takes a long time. Especially this one, if I just put it on something on the ground, it lasts almost 2 minutes before I have to charge it up again, which is pretty good for a spinning top. So that's pretty cool. But it's still working. It just gets lower. I can still put it back up again. It'll just start slowly going down again.
Let it go below
Sorry, what?
Let it go below the horizon.
It can for a little while. Because it has a ball in there, it kind of holds it, so it can actually go when it's kind of hanging almost down.
Yeah, I wondered if that was.
But yeah, again, I don't want it to go too far because I don't want to break. Like I said, they're expensive. I had to order it from England too. They don't even make them in the United States, so I had to buy it in pounds. All right, but the North Celestial Pole is right here, right? Okay, the angle is what? 23.5 right now. That actually changes over time too. Okay. But over how long does it take for it to rotate around? In fact, there's a circle on here.
About 10,000.
26,000 years, roughly. It's 25,000 something. We're rounding it to 26. Okay. Why does that affect astronomers? Why do we care?
Because what we look at now compared to what we.
See, now it's almost perpendicular. It's almost getting below perpendicular. And it's still hanging in there.
That's pretty
Pretty cool, isn't it?
cool.
Physics is fun. There's all kinds of cool experiments you can do. This, you can make a balance on like a spring, like a typo blocker and all kinds of stuff. If you have two of them, you can hook them together and you can do all kinds of cool things too. But
Could your other one get that low or would it fall?
the other one didn't last long because somebody had dropped it and the bearing got messed up. So it didn't hold, wouldn't spin for very long. It would start making loud noises and just slow down. So
I was gonna say, I didn't think we saw that before, but.
yeah, no, I usually can't make it go that far, but. All right, but it matters to us because you move the North Celestial Pole around on the celestial sphere, what happens to our coordinate axis? Changes. It's kind of like saying all our latitude and longitude are measured from where the North Pole is, right? And where England is. If you moved England around, everybody's longitude would be messed up, right? The problem is that's what's happening in the sky. Their coordinate system is shifting because our north celestial pole is shifting. All right, and it takes 26,000 years to go around. About 13,000 years from now, it's going to be over here. It's going to be right next to this really bright star. This is Vega. We're going to talk about Vega today because it's a very important star. Very bright star, very high in the northern hemisphere. Makes it very easy to see. Okay. And in the past, if you were in my archaeoastronomy class, we talked about that star right there. Who remembers what the star that was? Thuban. Thuban.
Oh,
And what was important about Thuban? It was the North Star for whom? The Egyptians, and about 5,000 years ago, it was the North Star. That was when they built the pyramids. And they actually lined the shafts in their tunnel to that star. All right, the other thing that happens with it is not only does it change the North Celestial Pole, but you see this point right here. What's that point right there? The what? Equinox, which one? Vernal equinox, which is at what right ascension? 0 hours. Well, while this shifts, when the North Celestial Pole shifts, it rotates the ecliptic around the celestial equator. So right now, this intersection is currently in the constellation of Pisces. Means the sun is in constellation of Pisces on the vernal equinox about March 22nd. Remember, 0 hours is measured for that. But over 26,000 years, this will move all the way around. Okay? I think I have it going the wrong way. We'll move this way. Because we are currently in Pisces, but we're going to go to Aquarius, which is the next constellation. So astrologer people are saying we are in the age of Pisces, and we're almost into the age of Aquarius. Back in the 60s, they wrote a song called The Dawning of the Age of Aquarius. I don't know if you ever heard it. That's what it's based on. Now it's 700 years until we get there, so it's a long dawn. But it does shift it around. And you're shifting 0. So 0 hour shift. So all the right ascension of every single star and all the declinations of every single star changes all the time. Every single night it changes. The good thing is we know exactly how it changes. And so whenever you put in the right ascension and declination, you have to put in what we call an epoch. What year it was calculated. So for astronomers, we usually do things every 50 years. So when you say, oh, the star, you say right ascension of the star, and then you put the epoch, like 2000, and the declination would be 2000 epoch. Now, soon, we're going to switch to the, once you get more than halfway, you switch. So in 2025, we're going to switch to the 2050 epoch. Every 50 years you switch. Okay. So when you're putting in coordinates into a computer, and you say, oh, I want to look at this object that you can't see with your naked eye, but the telescope needs to know where to look, you have to put in the right ascension declination, and you have to put what year those are calculated in. Then the computer says, okay, that's where it was in 2000. It calculates where it is tonight, 2021. It takes into account all the shifting. Back when I started doing astronomy, before we had fancy computers that could do all this, you had to do all that calculating yourself. It was called precessing your coordinates. So you would look up the coordinates, and then you would have to go use this formula, figure out what that night the right ascension declination would have to be. Nowadays, you don't have to do that. The computer takes care of all that for you. But you need to know that that's an effect and it changes things all the time. Another 26,000 years, it comes back to where it was. Okay. All right. That's precession. So what I really want you to get out of there is not only does it change the position of the North Celestial Pole, South Celestial Pole, but it changes the position of the equinoxes. They rotate around. All right, tonight we're going to talk about quantifying light. This is another chapter in your book. What does it mean to quantify something? What to it?
Give it a number.
Give it a number. That's what we want. We want to give it a number. In this case, we want to measure the brightness of objects. And we want to quantify that. We want that to be a number. So you can say, oh, this is brighter than this, and how many times brighter is it? Okay. Now, this was done by a, I'm not sure I'm spelling that right. By an ancient Greek astronomer, the first one to do this, guy named Hipparchus. I can't remember whether it's 1P or 2P. So if you look it up, try it both ways. But he was around a couple hundred BC, and he was really our first true astronomer. He was the one that started saying, okay, I'm going to watch the stars. I'm going to calculate the position. I'm going to calculate the positions of the planets. He created this dome where he marked all the positions of the stars. He was the first one actually to figure out that we know of, that figured out precession. Because he realized he got the position of all these stars in his coordinate system, and he realized they were all changing, and they're all changing together, which means the coordinate system is changing. And so he determined it. In fact, he determined out that it had a period of 26,000 years. He also cataloged a whole bunch of stars. He was the one that named a lot of stars that weren't named at that time, or he took the names and wrote them down for the first time. Might have been oral tradition, he wrote it down, but that's where we got a lot of the star names from. He was Greek. And he was the first one to say, okay, I'm going to categorize these by brightness. Now, back then, they didn't have any instruments. Nothing to actually measure how bright light was. So he would just look at it with his eye. And he would look at a star and say, oh, well, that one looks half as bright as that one, which is hard to do. But that's what he did. But he said, okay, I have to have a standard star. I'm going to compare everything to my standard star. What was the standard star? Vega. Why? Well, because it's nice and high in the sky for people at our latitude. Greece is about our latitude. In fact, it's a little further north than we are, but it's easy to see in the sky. It was easy to compare to. So we called Vega brightness magnitude of 1. Nowadays in our system, it's not exactly 1. It was supposed to be, everything was supposed to be compared to it. But then we realized that there's some weird things going on. Hey, it probably wasn't the best choice, but we still use it. Actually, we have a system now that's not defined by one star, but it's defined by the whole stars in the sky. We've been studying for so long, we know the brightness of all the stars, that the combined system defines our brightness scale. But then if he saw another star half as bright, he called that magnitude 2. It was half as bright. Did I spell it right? Or was I not even close? Oh, yeah, I wasn't even close. It did have 2 P's, but it's like this. Is that right? Yeah. I think I got messed up because they actually made a satellite that they launched that was orbiting the Earth. They called it Hipparchus. It was named after him, but they spelled it different because it was also an acronym. Whatever. This is the guy. All right. All right, so the second magnitude stars were supposedly half as bright as the first magnitude. And then third magnitude stars were half as bright as second magnitude stars. So they were half as bright again, but that made them 1/4 as bright as first magnitude stars. And then fourth magnitude stars were half as bright again, which made it 1/8. And you see it's going up by the power of 1/2 to the n, right? So it's powered. This is a really confusing way to do it. In fact, it's probably the most confusing scale you can have because it's an inverse logarithmic scale, right? Because it's power scale. which is confusing. And he got down to magnitude 6, and he realized he couldn't see anything any fainter. So the limit with your naked eye was you could go from 1 to 6. Are there stars brighter than Vega? Yes, there are. It's not the brightest star in the sky. So we have something that goes the other way. You can have magnitude 0, you can have magnitude -1, so on. All right, nowadays, to quantify this, make it much more logical, we realized that this system didn't really match. So what we do now, we say that every 5 magnitudes in brightness is equal to 100 times difference in brightness. What that really means is that instead of it first magnitude, the second magnitude being half as bright, that's not actually it. What we're really going to do is we're going to take the 5th root of 100. Right? Because over 5 magnitudes, you have to multiply together to make 100. So you have to take the 5th root of 100 to get the value. Well, that ends up being approximately 2.512. It's irrational, it goes on forever, but 2.512 is the acronym for us. So what this really means, the second magnitude stars are actually 1 over 2.512 times as bright as the first magnitude. And these would be 1 over 2.512 again, or 1 over 2.512 squared if you go to the third magnitude, and so on. Okay, so if I was to ask you and say, oh, hey, star A has a magnitude of 5.8, star B has a magnitude of 1.7. Which star is brighter? And how much brighter? Notice it's an inverse logarithmic. The inverse means that the smaller the number, the brighter the star. So which of those is brighter?
B.
Star B is the brighter star. And how many times brighter? How are we going to calculate that? What's that? I want to know exactly how many times brighter it is.
Multiply 4.15.
All right, so you take the difference first, right? So you subtract them, and you get 4.1. What do you do with that 4.1? No, remember it's powers.
Oh, would it be 1 over the 2.51 to that power?
Yeah, or we could just do this to that power, right?
Oh, yeah.
And we just flip it around and say, so yes, then you take 2.152 and you raise it to the 4.1 power. We got a calculator? What do you get when you raise that 2.512 to the 4.1 power?
46.7, 43.7.
43.7, good enough. How did I know it was less than 100 times brighter? Less than 5 magnitudes, right? If it was 5 magnitudes, it should be exactly 100. But you're like, oh, it's 4.1, it's close, but remember it's logarithmic. So it goes up and then it jumps up. So by the time you got to 5, it would hit 100, right? Better, or we did something wrong. Okay. All right. These magnitudes are called parent magnitude. Meaning, that's what it appears if you go outside at night. We usually designate that with lowercase m. The brightest star, parent magnitude is Sirius. What's its magnitude? Negative what? Yeah, negative 1 point something. I think negative 1.4 or something like that. Okay. Are there things brighter than Sirius? And you looked at it last week. Planets, right? Jupiter and Venus. Now the planets vary, but they can get up to about -4. And we can go higher than that. You go to the full moon. And the moon obviously varies too, but full moon gets up to about -12. The sun is about -29. Let's go the other way. Limit with just your eye is 6.
We don't have unit for that, or it's just number?
It's magnitudes. So it's 6 magnitudes. So that's the unit, is magnitude. Okay, it's kind of confusing, but that's what it
Where
is.
do you get negative from? Like we went down like 0 point something something.
So Vega's in here at 1, right? Okay. Or let's do this. Your eye, right? Your eye can see to a limit of 6, but your eye can actually see the sun as well, right? This is one of the things that makes your eye truly amazing. Is that it can see a massive range in brightness, can it? How many times brighter is the sun than the faintest star we can see? Yeah, but a lot doesn't work well on a test. I want a number. We're gonna do the same thing we did here, right? Let's do 6, and you've got to subtract -29. What happens when you subtract? You get 2.512 to the 35th, right? Or we also know every 5 magnitudes is 100 times, right? How many 5s go into 35? 7. So that's just 100 to the 7th power, which is 10 to the 14th power, or what number is that?
100 billion?
Millions, billions,
100
trillion. That is what's amazing about our eyes, our range that we can see brightness. It's actually truly amazing. we can't make instruments that do that very well. All right, we can make instruments that are really good at faint, really good at bright, but it's hard to make one that goes bright to faint, right? So that's one of the things that our eye is very, very good at. Same idea though, right? Faintest object we've ever seen, well, it may have been fainter now, it's hard to keep up. But the Hubble Space Telescope is in the deep field image where it shot a picture for like 7 straight days in the same spot. Got down to about magnitude 30, which is the faintest thing we've ever seen.
Without telescope?
With the telescope, with any instrument ever, that's the faintest that has ever been seen. Now, we're hoping to beat that when the James Webb Telescope gets launched. And it goes out there and starts a way bigger telescope, and if you shoot for a longer time, you should even get fainter than that. But so these are all paramagnitudes. This is what we're going to talk about mostly in this class, because that's what we see, right? When we go out there. But there are other magnitudes. There's absolute magnitude. And we usually do this as capital M. Absolute, yeah.
How did Marcus measure? You just kind of eyeball?
Yeah. How did he come up with the paramagnitude?
Yeah.
Yeah, I look at that and go, okay, that one looks, yeah, it looks half as bright as that. And then he would look at that one and goes, oh, that looks half as bright as that one. Not very precise, but you know, that's what you did when that's all you had, right? Absolute magnitude was created by astronomers, and it wasn't created until 1900s or so, early 1900s, because it took that long for us to have instruments to figure out that stars weren't all the same brightness. For a long time, that's what they thought. They said, oh, they're all the same brightness, but they're not. And they say, oh, well, they're also not the same distance. Remember, they thought they were celestial sphere, they're all like glued to a glass plate now. So it took us a while to get it figured out, and then we realized that, oh, there's distance and there's brightness. Some are brighter because they're close, like Sirius. It's actually a very close star to us, which is why it's so bright. It's only about 6 or 7 light years away, one of the brightest, closer stars to us. And some are bright just because they're really bright. Like Betelgeuse, it's 400 light years away, but it's still one of our brightest stars in the sky because it just pumps out a lot of energy. Okay, so that's where absolute magnitude came in. This is the brightness at 10 parsecs. Everybody know what a parsec is?
3 point something like this.
3.26 light years.
1 degree of parallax, right?
Yes, 1 arc second of arc. Yes. So-
Williams did his job.
Yes, he
Drill
did.
that.
Good. Drill that into it. Yes, 1 arc second of parallax is 10 parsecs, equivalent to 10 parsecs away. There's actually not that many stars that are closer to 10 parsecs, 30 light years to us. That's actually not many. A lot of them are real faint, hard to see. But what it says is if we could take all the stars in the sky, we could move them all to 10 parsecs away, then we would just compare how much brightness they're actually giving out. Okay? How bright the star would be. That's what absolute magnitude is. Now the absolute magnitude of the sun is about it's like 4.86 or so. Meaning if we were 10 parsecs away, it would be a fairly faint star. You could see it, but it wouldn't be too exciting. All right. Okay. But if we got within 10 parsecs of like Betelgeuse, it would be really bright. It's already bright in our sky, and we're, 100 some parsecs away from it. All right, we're going to talk more about these, how these are used later. Okay, why they're important. Right now, we're just going to talk about light. All right, and we also are going to talk about UBVRI magnitudes. Actually, nowadays there's more ones than this too, but there's BG something. But I'm going to talk about this one because the idea is the same. The idea is if you have light, U stands for ultraviolet, B is blue, V is green,
Visible.
R is,
Red.
I is infrared. So what we're going to do, what they did at a telescope is start saying, okay, we're going to measure how much light comes through filters that only let that part of the spectrum through. So this only lets part of the spectrum through in ultraviolet. This only lets blue. This is green. V came from visual, but green is the center of our spectrum. If you have a V filter, it's actually just a green filter. And this is red. This is infrared. And it actually goes on. You have J, K, and L that go on when you get into the infrared and pushes into far infrared. But what we can do is if we have a star, if you remember stars are basically black bodies. Meaning when they give off light, the light they give off at different wavelengths is a function only of their temperature. So if you have a really bright hot star, one that's like at a surface temperature of 20,000 degrees Kelvin. Hopefully this is review for you, right? You should have had this in some astronomy class somewhere. And a cool star is only a couple thousand degrees Kelvin. Talking about the surface temperature. And a star in the middle, not very accurate, but you get the idea. It's like this. And it would be a green star. And this would be about 5,000 degrees Kelvin or so. Now, in the visible part of the spectrum, right here, this is ultraviolet on this side. This is infrared on this side. Right? So, to us, a blue star appears blue because it's really hot, so most of its energy is coming out here on the blue side of the spectrum. Green star, we don't see green stars. The stars we see are white, actually, because our eyes, remember, add light waves together. And so when we have pretty much equal all the way across, we see that as white light. That's just the way our eyes work. Okay? And down here, this peaks on the red side. See, it goes up on the red side. So red stars are cool, blue stars are hot. This should be reviewed from some class you took, right? Hopefully everybody talked about that by fact. Okay. The idea with the UBVRI, let's just look at B and V, is if we only look at different parts of the spectrum. So this is the B part, this is the V part. If you look at this blue star, the hot star, it's going to be brighter in blue than in visual, right? Brighter in B than in V. In the green, they're going to be about equal. In the red, it's going to be fainter in the blue and brighter in the green. So astronomers realized, okay, if I can just measure the star's magnitude in these two different filters, I can figure out exactly what color it is. If I can figure out the color, I can figure out the temperature. So they created this index called the B minus V index. And you can do this with any of them, but B minus V is the most common. Yeah. Meaning you can do V minus R or R minus I, or you can subtract any of them because they're going to be different parts of the spectrum. If you're dealing with like white dwarfs, you're way up here in the U and B because they're very, very hot. And if you're dealing with cool stars, you deal down here in this end usually. So it depends on what you're looking at too. But a B minus V for a blue star, is that going to be positive or negative? For a blue star, which is brighter, blue or green? B or V, which is the brighter magnitude? Blue. Brighter though is
Oh, this, yeah.
the smaller number, right? So that means this number, the smaller than that one, is going to be negative. So blue stars are usually less than 0, or right around 0 or less. Okay. What about a red star? For a red star, you get significantly more light in the green than you do in the blue. This is usually greater than about 1. 1.5. I mean, it's not an exact number, right? Okay. And the ones in between here, to our eyes, usually appear pretty white. Okay. Now you get all ranges. Before you get to red, it actually turns to yellow, and then to orange, and then to red, and then to very red. All right, it's the same thing with blue. It doesn't go white to blue. It kind of varies towards that. Okay. But can we see colors and stars? Yeah, absolutely. In fact, if it's clear tonight, we will see doesn't look good. So my spotter took a picture of the clouds. So I don't think we're going to be able to do it tonight, unfortunately. So we'll do this next week. But next week, what I'm gonna do, I'm gonna tell you what to do for next week, and we'll do next time we go out. Is I want you to look at different stars that have very specific colors, and to see if you can see the colors of the stars. Yeah. And you can see, I mean, you can see colors that start with your naked eye too. You can see a star that looks a little bit blue, and you can see red stars. Reds are actually easier to see than blue usually. Yeah.
Are there some stars that are factoring out, the way our brain interprets colors? Are there some stars that you could like name that we might know that would be green to like an alien that didn't add colors?
Oh yeah, there's a lot. I mean, that's what our sun would be.
Really?
Yeah, our sun, our eyes, right, were evolved because we lived on this planet around this star, so that our eyes peak exactly at the center, which means technically our sun is a green star. But our eyes don't work that way. They add up all the light together, and we say, oh, if we put all the colors together, then we get white. But if an alien could separate out the colors, they would see our stars. And there are some people that claim to see green stars. But I think what they really see is there are peculiar things like planetary nebulas and stuff like that that actually give out green, but the green's coming from the glow of the gas, not from an actual star. But there's some that claim they see purple stars and all that. In reality, I've been looking forever and I don't see anything like that. But people with different eyes, if I say red, you might be seeing something different than what I see. I don't know. That's always a challenge. And if you're colorblind, then I really don't know what you're seeing, right? Especially what's funny is the most common color blindness is red-green, is they can't separate red and green. What do we use for stoplights?
Red and
Red and green, the ones that people can't separate. Doesn't make much sense, does it? We'll talk about that. We're going to talk about detectors and how our eyes work in a couple of weeks. So, all right. So, basically, I want you to know this, right? If it's V minus V is less than 0, right around 0 or less, it's going to be blue star. If it's going to be in between here, it's going to be white. As you get towards 1, it's going to start to turn red. It's going to actually start to turn yellow and orange first. And then red, these can go all the way up to 2 or greater here. So then it goes really red. You see more really red stars than you see really blue stars. Red's easier to pick out too. One of our challenges, and the reason humans have problems, is we can't see colors very well at low light. When it gets really faint and you go to your night vision, you actually can't pick out colors as well. So that's why when you take a picture of the sky, you say, oh, look at all those colored stars. But when you look out there with your sky eye, you go, well, they all kind of look white to me. All right. So far, so good. How does this relate to spectral types? I know I'm going over this quick, but I'm hoping you had all this in astronomy 1303 class at one time, right? Hopefully. Anybody remember their spectral types? You're in my class, you better remember them. Yes, that's good. There's ways to remember this, right? The most famous one is, oh, be a fine girl, kiss me. Or, oh, be a fine guy, kiss me, whichever way you want to go. Yeah. Or my favorite is, oh boy, a fantastic guy, Kent Montgomery. Well, they put my initials in there. What else could I do? All right. What are these?
Letters.
Yes.
Brightness compared to velocity.
Yeah, that's what they end up being equated to. But where do they come from?
Aren't they arbitrary?
They, well, now they're temperature. Originally, they weren't.
Oh,
Originally, they took spectra of all these stars. So they spread it out and they saw that they all had these nice absorption lines. And they started saying, okay, what are we going to do with all these? This is Harvard Observatory back in the late 1800s. And they gave them to all these women because they hired them to say, okay, what are you going to do with this? And they said, well, we don't know. They didn't know what it meant. But they realized that different stars had different ones. So they just put them in categories. They say, oh, those look the same. Let's call that group A. These look slightly different than group B. And they just went and stuck them in these categories. It wasn't until later that we figured out that their categories didn't have anything to do with anything. And that when we rearranged their categories and got rid of the ones that were extra that didn't really exist, we came down to these 7 and then we rearranged them according to temperature. And that's why we have O, B, A, F, G, K, M. Kind of weird, but that's how we ended up there. Okay. These on this side are very hot. This side, they're very cool. Okay. These are hot stars, these are cool stars. Where's the sun?
G.
G what?
G2.
G2, yeah. So we split each of these into 10 other ones. So it goes O0 to O9, B0 to B9, so on. G2 is where the sun is. The sun is right here. Sorry, G2. So, okay. What's this have to do with brightness? Well, if we look over here, this side has B minus V of what? Yeah, these get up to very high B minus V's, okay? Grade, definitely grade 1, closer to 2 when you get here, way out here to the M's. Over here, these have B minus V of, yeah, it's negative actually. These get to -1/2 or so but over here on this side. So not only does B minus V tell us their color, but it also can tell us their spectral type. Okay? Because it's a function, they're similar functions. Now it gets more complicated. You should have talked about in your other class the difference between main sequence stars and giant stars and supergiant stars. So it's a little more complicated, but spectral type directly corresponds to temperature. Temperature directly corresponds to your B minus V magnitude, which corresponds to your color. See how all that ties together? Hopefully. That's good. Now our sun, right here, when we see it in the sky, it actually looks a tinge yellow to us. Why is it yellow? Because of our atmosphere. Astronauts out in space, when they get above the atmosphere, say that the sun is just pure white. They don't see anything, it's pure white. It's our atmosphere that filters out some of the blue, which actually makes it tend towards the yellow color. All right. All right, so next time you go out observing, these are the stars that I want you to observe. Edith, which has a B minus B of 1.83, so what color is that going to be? It's red, yes, definitely red. Then we want you to do, this is the Smithsonian Astrophysical Observatory catalog 33693. This is the garnet star. Anybody know what a garnet is?
Yes.
Yeah, it's a red stone. Looks kind of like a ruby, but it's a different kind of precious stone. It has a B minus V of 2.66. About as red as you can get. So it's a really deep red star. Then we're going to look at Merak, which is a B minus V of 1.91. Then I also want you to look at Alvarez. Which has a B minus V of negative 0.05, which would make it a blue star. And Gamma Cassiopeia, which is SAO 11482, B minus V minus 0.06. And then I also want you to look at SAO 70474, which has a B minus V of 1.21.
So it's SAU, what, to the Gamma Cassiopeia?
You think you can't read that?
Sorry.
Oh, that's all right. My writing is a little sloppy. 11482. Make sure you have all this written down. When you go out to the observatory, you're gonna have to plug these into that hand pad. And if you lined up your telescope properly, they should go right to that star. In theory.
So we're just gonna be like looking for it through that list, or is there like a search function or something?
Yeah, on the pad. I didn't show you all the options, but remember there was one that said solar system and all of a sudden plants came up? The one that says star. And the star comes up and then it gives you an option. You can go down to where it says SAO. You click on that. And then you put in this number. And then it'll find that star. Okay. For these, if you go under star, you can also go to named stars. And Enough and Merak and Alpharets will show up under named stars. I think you can also do it by Greek letter. Okay, this is Gamma Cas. What does gamma mean? It's the third brightest star in the constellation of Cassiopeia. So alpha would be first, alpha, beta, gamma, delta, epsilon, and so on. So they labeled all the stars by Greek letters according to brightness. This was done quite a while ago, but we still use that name. So like Alpha Orionis is Betelgeuse. Yeah. All right, I also want one more. Alberio. Which is the eye of the swan. It's a double star. So it's actually two stars, but they both have colors. So two different colored stars. You can see the colors very well, so they're fun to look at. All right.
What was the double star that you told us to look for in, I don't know if you told everybody what this does.
What did I tell you? Oh, I told you to look at Mizars.
Yeah, and there were two.
Yeah, Mizar is interesting because it's a double star, but you can see with your naked eye. There's a star and another one right on the brightest. But when you look at it with a telescope, each of those stars fits into two more stars. So you can have, well, actually, this one splits into, I don't think this one does. But there's one in Vega, in Lyra, that's a double-double, where you see there's two stars, but then when you go on the big telescope, it's actually two, and it becomes four stars. And then after you're done with this, the next week we go out, we will do double stars. Because the double stars are a good way to test your telescope and how good you can see, whether you can separate them when they're a few arc seconds across, separate. You have a question?
What's the B minus 3 of Alberio?
Well, I didn't put it down because there's actually two stars there. And I don't want you to know in advance what the colors are. So I'm not gonna tell you. I want you to look at it and figure it out for yourself. See what you see, okay? All right, questions about any of that? Let me make sure there's anything I did not cover that you need to know.
Doesn't Sirius B have an apparent match here, like 30?
No, not that faint, because you can see in a small telescope. Sirius B, if you hear, Sirius A would be the bright one you see with your naked eye. Sirius B is its companion. Yeah, it's a white dwarf companion. But you can see it in a small telescope, so it's, I don't think it's that much. I don't know what it is, but because I've seen it before. I think it's 30. All right, that's all I have for the day. Except another homework. Yes, I can give you more sheets, or I will be actually, because we're not going out there tonight anyway.
You know, we did that too.
Kind of perfect.
Okay, put it.
It's not- okay. I always do think that I'm saying it's easy to do.